Every advanced electronic system, from the motor drive inside an electric vehicle to the high-frequency mixers in a radar system, relies on diodes to govern the flow of energy. Standard circuit theory teaches a convenient shortcut. It tells us to treat the diode as a rigid, perfect one-way valve with a fixed 0.7-volt drop. You put voltage in, and it either conducts perfectly or blocks completely. Here is what that ideal model looks like on an oscilloscope, a pristine, rigid half-wave Tice. But rely on that theoretical model in a high-frequency or high-power environment, and the trace collapses into this, a messy reality of voltage spikes, ringing, and backward currents. To understand why it fails, we have to plunge deep inside the black epoxy package. A physical diode functions as a dynamic, nonlinear energy barrier, governed strictly by quantum mechanics and thermodynamics. We are going to build a diode atom by atom, map its behavior mathematically, and define exactly how its physical limitations dictate modern engineering. Mastering diode physics, specifically its high-speed parasitics and thermal dynamics, is the dividing line between understanding functional theory and designing reliable, professional hardware. Pure silicon is an insulator. Its atoms lock together in a crystal lattice, leaving very few free electrons. To make it conduct, we must introduce impurities in a process called doping. By adding pentavalent elements like phosphorus, we force extra free-moving electrons into the lattice, creating N-type silicon. By adding trivalent elements like boron, we create positively charged voids or holes, creating P-type silicon. When we fuse them together, we create a massive concentration gradient. Immediately, the negative electrons from the N side and the positive holes from the P side diffuse across the boundary, rushing to mix with one another. But as these moving charges cross the junction and recombine, they annihilate each other's mobility. They vanish as free carriers, leaving behind their parent atoms, which are now charged, rigidly locked, immobile ions. This creates a central void stripped of all free charge carriers. We call this the depletion region, and because it lacks free charges, it acts as a physical insulator. Those fixed atomic ions left behind aren't inert. The positive ions on the N side and negative ions on the P side lock together to generate a powerful internal electric field across the junction. This internal electric field pushes back against the moving carriers. It exerts a force that strictly opposes any further diffusion, eventually reaching a state of pure electrostatic equilibrium. We measure the strength of this equilibrium state as the barrier potential. For standard silicon, that barrier is approximately 0.7 volts. Notice that a diode achieves its directional behavior without a single drop of external power. It is an internal electrostatic force field generated entirely by its own atomic geometry. To make current flow, we have to manipulate that barrier. We do this through biasing, applying an external voltage to physically stretch or compress the depletion region. This split screen shows forward bias. When we connect a positive voltage to the P side and a negative to the N side, we push against the diode's internal electric field. On the right, the IV curve plots voltage on the x-axis and current on the y-axis. Initially, the current is negligible as the external voltage physically crushes the depletion barrier. The moment the external voltage exceeds that 0.7-volt barrier, the internal field collapses. An avalanche of majority carriers easily floods across the junction, and the current spikes steeply upward. To model this conduction mathematically, engineers use the Shockley diode equation, which calculates total diode current based on the applied external voltage. The critical component here is Euler's number. It proves that once the barrier is overcome, diode current increases exponentially, not linearly. A tiny increase in forward voltage results in a massive surge of current. If we flip the external voltage polarity, we enter reverse bias. Now, the external voltage adds to the internal electric field. The depletion region drastically widens, and the IV curve plots a flat line of zero current. This widened region acts as a thick dielectric wall. It blocks all forward flow, allowing only a microscopic leakage current of minority carriers to seep through. The macroscopic behavior of a diode, conducting or blocking, is simply the result of an external voltage either overpowering the internal electrostatic field or reinforcing it. In low-frequency circuits, this response seems immediate. But in high-frequency environments like switch-mode power supplies, polarity reversal is never physically instantaneous. When forward voltage pushes carriers across the junction, some electrons are momentarily stored deep inside the p-side lattice. If the voltage flips abruptly, these stored minority carriers don't just disappear, they are violently ripped back across the boundary. This causes a brief period where the diode fails to block reverse current. The time to physically sweep these stored carriers out of the junction is called reverse recovery time. On an oscilloscope, it manifests as a massive, unwanted negative current spike. Every time the diode switches, this reverse current spike generates heat and wastes energy, causing immense switching losses and efficiency degradation in high-speed circuits. While reverse recovery ruins high-speed switching, a reverse bias diode also exhibits a static parasitic behavior. In this state, it is physically identical to a capacitor. This effect is known as junction capacitance. The highly conducted P and N regions act as metal plates, and the widened, charge-free depletion region acts exactly like a dielectric spacer. At high frequencies, the diode behaves as a dynamic, analog energy storage device, a reality that requires active mitigation to ensure signal integrity. Passing massive forward current through a diode generates severe internal heat. The power dissipated as heat is simply the forward voltage drop multiplied by the current. This chart demonstrates how heat compromises the atomic structure. Silicon has a negative thermal coefficient, meaning as temperature rises, the forward voltage drops by about -2 millivolts per degree Celsius. The internal barrier physically weakens, and the IV curve shifts to the left. This thermal dependency creates a catastrophic feedback loop known as thermal runaway. Heat lowers the forward voltage. The lower voltage pulls more current. The higher current generates more heat, looping continuously until the component melts. To prevent this, PCB thermal management and heat sink sizing rely on the junction temperature equation. It proves that internal junction temperature is a direct function of power loss and the thermal resistance of the materials. Heat is one failure mode, voltage is another. If we apply extreme reverse voltage, the external electrostatic force becomes so severe that it physically shatters the internal barrier. This breakdown happens in two ways. Zener breakdown occurs when the electric field is strong enough to rip electrons directly out of their quantum bonds. Avalanche breakdown occurs when a single high-speed particle collides with the atomic structure, kinetically knocking free multiple particles in an explosive, cascading chain reaction. The stability of any power circuit depends on precise heat extraction. Left unmanaged, thermal energy directly compromises the diode's internal solid-state physics. We can apply these solid-state principles directly to circuit design. In low-frequency AC to DC conversion, standard silicon rectifiers easily handle high forward currents. This bridge rectifier uses 4 diodes and a smoothing capacitor to generate clean DC power, guided by the ripple voltage approximation equation. But attempt to use those same standard silicon diodes in a modern switch-mode power supply, and they will violently overheat. At switching frequencies of hundreds of kilohertz, the standard reverse recovery time creates too much power loss. The physical solution to these high-frequency parasitics is the Schottky diode. This diagram shows its internal architecture. Instead of a p-n boundary, it fuses a metal directly to an n-type semiconductor. Because the Schottky lacks p-type material entirely, it has zero minority carrier storage. There are no holes for electrons to get trapped in, which completely eliminates reverse recovery time, allowing for extreme switching speeds. Diodes are also used to manage the extreme physics of inductive energy. When power is removed from a relay coil or motor, the collapsing magnetic field generates a massive, destructive voltage spike. By placing a flyback diode in parallel with the inductive load, we create a safe path. It remains reverse biased during normal operation, but the moment the inductor generates its high voltage spike, it becomes forward biased, safely shunting the energy in a continuous loop until it dissipates. Designing reliable circuits requires discarding the elementary analogy of the one-way valve. True engineering relies on controlling energy barriers, anticipating thermal collapse, and respecting the raw solid-state physics embedded in every datasheet.